Okay, let's go ahead and talk about the preparation and properties of buffer solutions lab. This is a cool lab. I especially like the last part of it. The first part is useful because it shows, it just gives you kind of a good idea of what happens when you add strong acid or strong base to a non-buffered solution versus when it's in a buffered solution. But I think the real value in this is just showing you how to prepare a buffer solution at a specific pH. So the first part of this, the introduction, is basically just talking about the derivation of Henderson-Hasselbalch, and you can see down at the bottom here, you end up with the Henderson-Hasselbalch equation, pH equals pKa plus the log of the base concentration over the acid concentration, and that's just really, it's an important equation for buffer solutions. I guess this is kind of nice. I don't know, again, it's kind of just plugging into a formula without real understanding. You can get to this by writing the conjugate expression, I guess, for a weak base equation. But if you have a basic buffer, then you can actually use this equation, and they've just sort of rearranged this so that you've got 14 minus the pKb plus the log of the base concentration over the acid concentration. So that will get you to your pOH, your pH. But essentially, I mean, it's just, if you understood that the Kb expression is going to give you the pOH instead of the pH, then you just take 14 minus that at the end. So again, I don't know if that's absolutely necessary, but there it is. So this just is giving you an overview of some stuff, and then we get to the pre-lab questions here. It says the pH of a solution is measured to be 3.50. Calculate the hydrogen ion concentration. Okay, and hopefully we can do that. Remember, when you're trying to find the H plus concentration from the pH, you're basically just 10ing this number, so 10 to the negative 3.50, and that would give you your H plus concentration. I don't think I really need to go over that. Fill in the chart below with the formula of the missing conjugate acid or base. Okay, and again, I think we can do this. I mean, we've been doing this for the last couple of chapters, so all you're doing there with that conjugate acid, just think about what acetic acid is going to look like after it has given away its hydrogen, and that's going to be the conjugate base. Okay, and then likewise with the conjugate bases, think about what's going to happen to them after they have taken a hydrogen from water, and that's going to be your conjugate acid. Okay, I really think you guys can do that just fine on your own. I don't need to walk you through that. Number 3 here. Oops. A buffer is prepared using the conjugate acid-base pair acetic acid and acetate, which is a very common one. Write the chemical equations showing the reactions that take place when H plus and OH minus are added to the buffer. Okay, so we're going to write 2 different equations here is what they're looking for. They're looking for an equation when you add the H plus, and then they're also looking for an equation when you add the OH minus, okay? Strong acid and then strong base. So again, you just have to think about what the H plus is going to react with here when you put it into the solution. The H plus probably won't react with the acetic acid because that's 2 acids, but it would react with the acetate because the acetate is a weak base, okay? So what you end up with here is you've got H plus your acetate, C2H3O2 minus. Forward arrow, because this is a strong acid that we're putting into the solution, that's going to make acetic acid, C2H3O2. Okay, so there's your equation for the first one. And then for the OH minus, when you add that into that buffer solution, it's going to react with the acetic acid. So you've got HC2H3O2. And that is, whoops, probably should put what it's reacting with here. It's going to react with the OH minus, and when it does that, this hydrogen goes over to the OH minus, makes H2O, and then you're going to end up with the acetate ion, C2H3O2 minus. Okay, so there's your chemical reactions for those 2. They just wanted you to write what happens when you add those to the solution. And then you've got to realize, and you don't have to write this on this question, but what you have to realize then is that this, in the top example here, this acetic acid is then going to start doing equilibrium. which I guess you can write that reaction if you want to. I mean, because technically that's what's going to happen next, is that acetic acid is now going to start doing equilibrium, and it's going to, a little bit of it is going to dissociate into H plus and C2H3O2 minus. Okay, and then likewise on this bottom one, after this acetate ion is created, then a little bit of that is going to pull a hydrogen off of water and make the acetic acid and the OH minus. Okay, so that's what's happening on number 3 here. Number 4 is asking, acetic acid has a Ka value of 1.8 times 10 to the negative fifth. How many grams of sodium acetate would have to be added to 100 milliliters to prepare a buffer with a pH of 4.50? Okay, so this is a little bit tricky. Usually we're trying to figure out the pH of the buffer solution, but now they're having us go backwards. So this is kind of a tough question. It's not too bad if you remember Henderson-Hasselbalch. That's basically what you're plugging into here. So we would just use the pH equals pKa formula plus the log of the base concentration over the acid concentration. Let's see here, the pKa, I'm looking for my calculator, and it's way over here. All right, so if you take the negative log, actually I think this is 4.74. Let me just check and make sure of that. If you take the negative log of the 1.8 times 10 to the negative fifth, yeah, 4.74. So that's your pKa plus the log of the base concentration over the acid concentration. All right. Now we know the acid concentration here, so our base concentration is essentially our X here. Okay, over 0.10. Okay. So what we can actually do here is to get rid of this log, because that's, you know, that's awkward in this equation, is we can 10 everything, or you can kind of remember where this equation came from in the first place. It really comes from the Ka expression, right? So Ka is equal to, in this particular case, we've got our H plus times our C2H3O2 minus all over HC2H3O2. Okay, and again, that comes from the dissociation of acetic acid. So that, you know, your equilibrium here, C2H3O2, in equilibrium with H plus C2H3O2 minus. Okay, so then if we plug everything in here, the things that we know the H plus concentration because we know the pH. We know the acetic acid concentration, okay, and we're just trying to figure out the acetate concentration that we would need to put in there in order to make a buffer that has the H plus concentration of you know, corresponding to the pH of 4.50. So this might be the easiest way to solve this. Again, if you 10 this equation up at the top here, if you 10 everything in that equation, then it should give you this bottom equation here again. Now, if we rearrange this to, you know, to find what we're solving for, see, we're going to end up with the C2H3O2 minus concentration is equal to Ka times the C2H3O2 over the H plus concentration. Okay, and so then we just plug in everything that we know, and we can solve for the acetate ion concentration. Now, that's not the answer to the question, but that will help us answer the question. So again, our Ka is 1.8 times 10 to the negative fifth. Let me see if I have room for this. 1.8 times 10 to the negative fifth times 0.1, because that's our acetic acid concentration. Now, again, we're assuming that so little of that dissociates that even in our equilibrium solution, we still have about 0.1 concentration. Okay, that's, I think with that Ka, that's a safe assumption. and then we're going to divide that by the H plus concentration in the solution, which we're going to use the 4.50 pH to figure out our H plus concentration, which is going to be 3.16 times 10 to the negative fifth. Okay, so once we do all that, and we figure out what our acetate ion concentration is, we should get 0.05, let's see how many sig figs are we working with here? 2. So 0.057 molar for our acetate ion concentration here. Okay, now again, that is not what the question is asking us. It's asking us how many grams of this do we need. So I'm going to get rid of some of this stuff so that we can think about this here. Okay, so they're wanting to know how many grams would have to be added to 100 milliliters of solution to prepare that buffer. So the first thing we're probably going to have to figure out is the number of moles. Now, if you remember, molarity equals moles over liters. Okay, so if we have the molarity and we have the volume, then we should be able to figure out the number of moles just by multiplying those two. So we take 0.057 molar times 0.100 liters, okay, because 100 milliliters is 0.1 liter. So 0.0057 moles of the acetate ion, okay. So then once we know that, we can take that 0.0057 moles of C2H3O2 minus, and then just do a little stoichiometry or dimensional analysis here, I guess. To go from grams to moles, you'd have to figure out the molar mass of the acetate there, and that's going to give you the number of grams that you need to make that buffer solution. Okay, so kind of a complicated, long process there, but that's going to give you how many grams you need to add in order to get to that buffer with a pH of 4.5, which, you know, in chemistry circles, every once in a while, it could be useful to make a buffer with a very specific pH, depending on what you're trying to do with it. So that's, I don't know, I'm not thinking of a practical application of that off the top of my head, but you might potentially use that in some of your college chemistry classes when you're trying to create a buffer solution. So that's how you would answer those pre-lab questions, okay? Now, for the procedure here, we're probably going to have to divide and conquer. So I'm going to have half of your lab group working on part 1 and part 2, which should go pretty fast. You have all the materials for that. And the nice thing about this one is we can kind of share pH meters because there are only specific times when you're actually measuring the pH of your solution. So hopefully we have enough working pH meters that we can do that. But part 1 and 2, one group should be able to finish that fairly easily, and then I'm going to have, I should say, one half of your group. Then I'm going to have the other half of your group working on the part 3, preparation of a buffer of a given pH. This is the part that's going to take a little bit longer, and I don't think you'd have time to do all 3 parts probably in one day, but if you're dividing it, if there's a group that's working on part 3 from the very beginning, then you should be able to finish it. So the instructions here are basically telling you what to do. You're going to do something very similar at the beginning of this to what you did in the last lab that we did, where you were trying to find the Ka of a weak acid. You are basically taking part of that weak acid after you've prepared it, and this is going to be an unknown, okay? So you got to find the Ka of it first. That's the first thing that you have to do. So what you're going to do is basically make a buffer solution that is exactly equal in its concentration of acid and conjugate base, and when that happens, remember the pH is equal to the pKa. So then when you measure the pH of that solution, then you're going to, that's going to tell you the pKa of your acid, and then if you 10 that, that will tell you the Ka, all right, which will help you with some later calculations. But it really is basically the same procedure as what you did before. You're going to take about half of it, you're going to neutralize it with sodium hydroxide, titrate to the end point, and you don't have to do this using a burette necessarily, but you're gonna go until you get the color change, okay, and then you're going to add that back into the original solution, because once you get the color change, that means you've completely changed all of that acid into its conjugate base. So then you add equal volumes of the acid and the conjugate base together, then your pH is equal to your pKa, okay? And then what you have to do, I'm going to assign you a specific pH of buffer that you have to prepare, okay? And so then what you have to do is you have to figure out what volume of conjugate base and conjugate acid you need to add together in order to make that particular pH. Okay, now this formula is, this is helpful, okay, because we can assume the concentrations are going to be the same. The volume of the conjugate base over the volume of the conjugate acid, that ratio is going to be the same, okay? So then they're saying X is the volume of the acid and 50 minus X is the volume of the base that you need. So you can kind of figure that out. Let me see here. When it says to calculate the... Yeah, see, I'm gonna have to explain this in class anyway, so I'm not real worried about you figuring this out ahead of time, because obviously once I give you your pH, then you're gonna have to do a quick calculation in class to figure this out. I guess maybe we could talk about it a little bit now, just so you're prepared in case you do watch the Prelab before. Where are your data tables here? Okay. So down here on the data table 3, so after you know your assigned pH, then you're going to do a calculation that's very similar to number 4 in the Prelab. Okay, so after I give you a certain pH, then you can know the ratio of acid to base that you're going to need. Okay, and my recommendation for that is that you don't necessarily use Henderson-Hasselbalch. I would use the Ka equals, and because this is a weak acid, we've got, I'm sorry, HA is on the bottom of the weak acid equilibrium, because basically your equation is HA yields H plus plus A minus. So H plus and A minus are on the top here. HA is on the bottom. Okay. And so what you're going to do here, if you rearrange this thing so that you've got your A minus over HA, if you take your Ka divided by your H plus concentration, that's going to be equal to the A minus over the HA concentration. All right, so if you know what pH you're supposed to have and you know your pKa, then you can figure out your Ka, you can figure out your H plus, and so you know what your ratio needs to be, okay? And so once you know your ratio, then you can figure out the volume of the acid and the base that you need to add into that solution. Okay, once you know what this value should be, then you can come back up here. I'm going to have to erase this because it's going to follow me. But once you know that ratio, then you can come back up here and look at what they've written in the instructions on part 3. And what they're telling you here is once you know this, okay, that's going to be equal to the volume of the conjugate base over the volume of the conjugate acid. And so you can use this 50 minus X over X is equal to, you know, whatever your base over acid ratio ends up being. Okay. And then you can figure out how much of each of these you need to add. Okay, so that's the equation that you would need to use for that. Hopefully that makes sense. If not, I can explain it a little bit more in class. Once you figure out the volume of your weak acid and conjugate base that you need to put in there, you're going to actually do it, and then you're going to measure it with the pH meter and see how close your measured pH comes to the assigned pH that I gave you up here. Okay? And so hopefully that makes sense, and hopefully you get pretty close to the calculation you're supposed to, or the pH that you're supposed to have there. Okay. Postlab question number 1. In step 1, how did the strong acid affect the pH of distilled water? You can answer that question. Compare the pH values of steps 1 and 2. Did the addition of NaCl, a salt of a strong acid base, buffer the pH changes? Okay. And we already know the answer to that. We should. Because sodium, when you put it in, sodium ions, when you put them in water, don't do anything, and the chloride ions also don't do anything. So that's really not going to, it shouldn't help to buffer the pH changes. So your data should show that. But you're basically just talking about your data. And then 3 and 4, basically the exact same thing, except now they're asking about the strong base instead of the strong acid. Okay. Number 5, compare the pH values of steps 1 and 5. So now we're looking at, okay, we put strong acid into distilled water, and then we put strong acid into this buffer solution. Okay. And it's asking, how did the buffer affect the pH changes? So what you should see there, obviously, is you should see a much smaller pH change with the buffer solution, step 5, than you did in step 1. And then they're asking you to write a chemical equation to show the reaction of HCl with the buffer. That's, straight from the Prelab. Okay, we talked about how to write that equation on the Prelab, and we talked about that a lot in class as well. So I think you're fine there. Number 6, compare the pH values of steps 1 and 6. Okay, so again, now we're talking about when we added the base, how did the pH change? And again, you should see a lot less of a pH change with step 6 than you did with step 1. And then the pH values of steps 1 and 7, how did the ammonium ion buffer affect the pH changes with the HCl? Okay. And then again, 8 is asking about the ammonium buffer. So basically, you're just looking at your data and answering these questions. You can do 1 through 8 with no problem at all. Shouldn't take you very long to answer those questions. Number 9, did your prepared buffer match your assigned pH value? So this is just basically saying how well did you do at your calculation, and how well did you do with your measurements, and this is your chance to explain anything that might have gone wrong, explain why there might have been differences between your measured pH value and your assigned. And then number 10, comment on the ability of your prepared buffer to resist the change of pH when HCl and NaOH are added in step 25. So in other words, you're explaining why is it that a buffer can resist the pH change when you put the HCl and the NaOH into the solution, the strong acid and the strong base. Okay, those post-lab questions, really, they should not give you any trouble at all. There's really not even any calculations involved with those. They're just conceptual, asking you about your lab. So as long as you get the pre-lab questions and the calculations that you have to do within the lab itself, you should be fine on this one. Okay, that's it. We'll see you in class.